Hello, my name is Betty Du Bois, and I'm a network detective. Today I'll show you how I solved the case of the missing DNS load balancer. A customer of mine at an ISP asked for my help. It seems he was seeing errors in his DNS logs and getting complaints about slow DNS response times from his customers. He wanted to add another DNS server for load balancing, but was getting pushback from his boss about the cost. He needed concrete evidence that his DNS server was being overwhelmed and asked if I could prove it. Wanting to ensure valid delta times, I inserted a gigabit tap between the DNS server and the switch and began viewing the traffic with Pilot. I knew that I would want to be able to look at the file information in more detail back at my office, so I sent the data from my device to File. We'll use the saved file for the rest of this video. I'm going to take a three-pronged approach: network usage to find inappropriate traffic, DNS responses to find error codes, and then zero in on DNS response time to quantify slow. We'll start by looking at network usage by traffic type. I want to make sure there is not attack, spyware, or unnecessary protocol traffic against the DNS server, thereby causing the slow responses. Well, it's good to see that almost 98% of the traffic is DNS, which is exactly what we should expect. However, let's drill down on some of the extraneous traffic to see what it really is. I'll right-click on SNMP traffic and drill down to IP conversations to verify that it is simply management software from inside the ISP gathering statistics. The 10 addresses are internal to the ISP, but I'm not sure why there are so many. I'll make a note so that on my report, my customer can know to track down each of these internal addresses. We'll look at the unknown traffic next. I'll right-click and send it all to Wireshark. Notice the DNS server is always the destination address and that this is IP fragmented traffic. These are simply DNS responses that exceed the maximum transmission unit for the sender and are fragmented in normal fashion. No smoking gun here. We'll next focus on the web traffic. I'll right-click and drill down to IP conversations. Most of the traffic is to the IP address of our MRTG server, and that's expected. However, we do have a few straggler addresses, which is undoubtedly nuisance scanning traffic. I'll enter a note on this for the report, that this traffic should be blocked. Bearing in mind that the DNS server is outside the main firewall, I think we're going to find quite a bit of this type of traffic if we were to drill down for each of the additional traffic types in the view. I think we should recommend a simple port-based firewall, just for the DNS server. Blocking this extraneous traffic should help speed up its response time and keep it a lot safer. Now let's focus on the DNS traffic itself. I'm interested in the DNS errors that we've seen in the logs. I'll open the view DNS responses. 2.24 million of the responses were positive from the DNS server. That's a great sign. Format error means the client formatted the query incorrectly, and we're not worried about the clients. Name error means the name that the client requested doesn't exist. Again, a client issue that is not our concern. The over 104,000 server failures do concern me. While that's only 1/2 of 1%, it's high enough to warrant further investigation. I need to see if the error codes are happening throughout the time sample or are clustered together. I'll select server failure and drag and drop the DNS response view onto just that response code. In the responses over time graph, I can see that server failures are being sent throughout the almost 3-hour time sample. It's not a case of a burst of errors due to high utilization, but is consistently happening over time. I don't believe that the 1/2 of 1% ratio is enough to get approval for the new server. Now it's time to zero in on DNS response time. Remember, customer complaints are what prompted us to go on-site in the first place. I'll apply the DNS response time view to the original trace file. The average response time looks to be between 9 and 15 seconds. No wonder the customers were complaining. We need to remember how DNS actually works before we jump to the wrong conclusions. Bearing in mind that when a client makes a DNS query, the DNS server first looks to its cache for the response. Answers from cache should be very fast. If the server does not have the answer in cache, it must perform recursion, which is an iterative lookup. In other words, if the query is for www.casetech.com, it asks one of its root servers, who's www.casetech.com. It receives the name of the authoritative name server for the casetech.com domain as an answer. The server then asks the name server, who is www.casetech.com. As each server answers, they include authoritative resource records in their answer. The originating DNS server adds these records to its cache according to the time to live field in the answer. Once the originating DNS server has an answer for the host in the original query, it includes the learned authoritative resource records in its response to the original client. Therefore, no authority record means an answer is from cache. Now we need to know how many of the slow responses are because our server was waiting for other DNS responses during recursion, and how many are because the server itself is slow. I'm going to hold down my Control key while dragging the DNS response time view over the trace file. This makes the filter panel pop up, and I can apply either a Wireshark capture, Wireshark display, pilot, or time interval filter. The trace file is almost a gig in size. Pilot is much better equipped to handle filtering on such a large dataset, so I'll use one of my pilot filters. I'd like the view to be applied to both queries and responses, but only responses where there are no authoritative records, i.e. the DNS server is answering from cache. When answering from cache, response times measured here at the server should average 50 milliseconds, in my opinion. But our expectations are a lot lower when our DNS server has to perform recursion, since we have no control over the speed of the upstream DNS servers. Wow! Cached data average response times are actually slower than all DNS response times. Here is our smoking gun. Let's see if there's a pattern in the worst of the response times. Maybe they are only during high utilization or for only certain response codes. No, timing and response codes are in the same proportion for the worst response times as they are for all response times. The server simply can't keep up with the requests. I think we're ready to create our report. I know that the notes we've added will make it much easier to get that new DNS server. See you next time. I have to go see another customer who wants me to investigate a dropped VoIP call mystery. Learn more about Case Technology's pilot at www.casetech.com.